Hello Algebra 1, it's Miss DiLullo here, and today we are going to be solving 1 and 2 step equations. So by the end of this lesson, you will be able to solve 1 and 2 step equations using the properties of algebraic properties that we learned last week and the properties of equality that we are learning today. So let's get started. So when we are solving single variable linear equations, we want to make sure that we hold true to the power of an equal sign. An equal sign means that whatever is on the left side is exactly the same as whatever is on the right hand side. So let's say that we have a variable on the left hand side. That means that whatever can be plugged in for that variable must still make the equation true. So, what is our strategy for figuring out what that variable is? The key is we're going to isolate that variable. Once we isolate that variable, we will find out the truth and figure out what that variable should be in order to make that equation true. So let's take a look at this example, x plus 5 equals 12. As we learned last week about algebraic properties, we learned that how we would cancel addition would be to use subtraction because that would be our additive inverse. We are going to be using those properties that you learned last week to help isolate our variable. In this example, x plus 5 equals 12, I need to figure out what I can plug in for x in order to make this equation equal 12. So, how would we do that? I'm going to start by figuring out what I need to cancel addition, and that would be using subtraction. And I'll show you how in the next step. So in order to solve this, I'm going to start by drawing a line from the equal sign. This line is to help me and show me that whatever I'm doing on the left hand or right hand side on the equal sign needs to be done to the other. So you can see that you're doing it in two places in the equation. So now that I know what cancels with addition, using my additive inverse property, I am going to subtract 5 from positive 5. Now you can see that I've done an operation on the left-hand side of the line, so I need to do that same operation on the right-hand side. I'm still holding my equation equal. So using my algebraic properties, I know that positive 5 minus 5 will actually what I'm going to call zero out. Whenever you have something that goes away to equal 0, we're going to circle it and make a 0, so we know that it's not there anymore. Now we need to finish solving our equation. So in the next step, under the line that I drew to complete this equation, I'm going to bring down the x that I didn't use before. I'm going to bring down the equal sign and then do the operation of 12 minus 5. Well, 12 minus 5 is equal to 7, and now we can see that our x is completely isolated. So, technically, we should have figured out what we can plug into this equation to still make it true. Let's check. So, I'm going to take my original equation, x plus 5 is equal to 12, and use parentheses when plugging in. Plug in 7 for where x was. So now I can evaluate 7 plus 5 equals 12. Does 12 equal 12? Well, yeah, it does, so I'm going to put a smiley face there. So because I isolated the variable, I was able to see what x can be in order to make this equation true. So in addition to our algebraic properties, we're going to be using the properties of equality to verify why we add things to both sides or subtract, multiply, and divide to opposite sides of the equation. So the addition property of equality states that if a quantity is added to one side of the equation, it must be added to the other. The subtraction property, if a quantity is subtracted to one side of the equation, subtracted by, then it must be subtracted by the other. Multiplication property, if a quantity is multiplied on one side of the equation, then it must be multiplied on the other. And finally, division property. If a quantity is divided on one side of the equation, then it must be divided on the other. So these properties of equality explain why we do things to both sides of the equation. Without them, our equation wouldn't hold true to the equal sign. Let's do a problem together. So the first thing I'm going to do with this problem, x minus 12 is equal to 21, is draw a line from the equal sign. That lets me know that I need to follow my properties of equality. So in order to first isolate my variable, I need to get rid of the minus 12 that is attached to it. In order to do that, I'm going to zero it out using the additive inverse, which will be adding 12. Since I added 12 on the left side of the line, I'll add 12 to the right, and then make sure that negative 12 plus 12 zeroes out to 0. I'm left with an x on the left-hand side. Bring down my equal sign, and now I evaluate 21 plus 12, which is equal to 33. So my solution to number 1 is x is equal to 33. Let's try another problem. In number 2, we have 2x is equal to 50. I drew a line from the equal sign to again make sure that I'm following my properties of equality. Before I start, I want to make sure I know how this 2 is attached to the x, because in order to be doing my inverse operations, I need to know the initial operation being done. 2 is being multiplied by x. So in order to figure out how to get x by itself, I'm going to be dividing by 2, because now I'm using the multiplicative inverse. 2 divided by 2 is equal to positive 1. So instead of now canceling those out to equal 0, 2 divided by 2 is equal to 1. So I want you to notice the difference on the left side of the screen to the right. When you add and subtract things, those cancel out to be 0. But when you multiply and divide by their inverses, they equal 1. So 1x is equal to 50 divided by 2, which is 25. And technically we don't need the 1 there, so I'm going to just simplify to x is equal to 25. Now you can go ahead and plug these in back into the original equation, and you can do those on your calculator to just verify that you do indeed have the correct solution. Let's try a problem that originally starts with division. I have x divided by 5, which is equal to 7. So in order to appropriately show my work, I'm going to write the problem below so that I have enough room. So 1x over 5 is equal to 7. I put the 1 before the x so that I remember that there is a 1 on top there and not just the x. There's always that variable 1 in front of your variable x, y, whatever your variable is. So I'm going to draw a line from the equal sign to again make sure that I'm following my properties of equality. And now I need to isolate my x. So I can see that x is being multiplied by 1/5. So in order to make that go to a 1, I need to use the multiplicative inverse, which will be multiplying by the reciprocal. So that means that I'm going to multiply by 5 over 1 to both sides. Well, when you multiply 5 over 1 times 1 over 5, that goes to 1. So I 1 those out, and now I am left with just a 1 in front of my x, and that is equal to 7 over 1 times 5 over 1. Using my rules for multiplying fractions, 7 times 5 is equal to 35. 1 times 1 is equal to 1. So 1x is equal to 35. I can simplify that just a little bit more by taking away the 1 and just making x equal to 35. Now number 4 is very similar to number 3, although it doesn't look exactly the same. Whenever you are multiplying a fraction times an x, the x is really represented as a numerator in the fraction. So it is very similar to number 3. I would like for you guys to pause the video and try number 4 on your own. When you're ready, unpause the video to check your answer. X is equal to 27. Make sure you write down any questions if you have them, and we can go over that problem tomorrow. But what if there's more than one step in our equation? What if we can't just add, subtract, multiply, and divide right away to isolate the x? What do we cancel out first? Our first goal is always to zero out the constant. That means using our additive inverse in order to make that constant equal 0. Second, after the constant is 0, then you can 1 out the coefficient, and that means using the multiplicative inverse to have that equal 1 in front of your variable. That is always the last step that you do. So let's look at a few examples. In this initial equation, we have 5x plus 25 is equal to 100. So in order to begin solving this, I'm going to again draw my line from the equal sign. When I draw my line from the equal sign, the first thing I'm going to do is notice, how do I isolate my variable? What do I do first? Well, I have a constant of plus 25, so I need to get rid of that first. In order to zero out my plus 25, I'm going to subtract 25 to both sides. Plus 25 minus 25 zeroes out, so I am left with 5x is equal to 75. Finally, now that I have just the 5 being multiplied by the x, I'm going to use my multiplicative inverse and divide by 5 to 1 out the variable. So now I have 1x, which is equal to 15, which can be written as x is equal to 15. Let's do one more together. First, I'm going to draw my line from the equal sign, and then I'm going to start by adding 52 to both sides because 52 is my constant. Negative 52 plus 52 zeroes out, so I'm left with negative 2x, which is equal to 6 plus 52, which is 58. Now I need to 1 out my coefficient, so I'm going to divide by negative 2 on both sides. Negative 2 divided by negative 2 is 1, so I'm left with 1x, which is equal to negative 29. Remember that when you have a positive divided by a negative, that your answer will be negative. So my answer to number 2 is x is equal to negative 29. I'd like for you guys to try numbers 3 and 4 on your own first. So go ahead and pause the video, try numbers 3 and 4, then look back at the video to check your work and make sure that you did everything correctly. Be careful for number 4, there might be a coefficient ninja ready to come out and get you. After you're done with your work, go ahead and unpause the video to check your solution. If you have any questions over these problems, make sure that you write them down so that we are able to go over them in class tomorrow. Actually, next week. So, that's Ms. DiLullo signing out, and we'll see you next week.